Hi, I'm Sebastian Russo, and today we'll be talking about SF4, the molecules assigned for this chemistry project. First of all, we were assigned to draw the Lewis dot structure, and the final result will look like this, with 4 outer bonds and 1 lone pair. Secondly, there will be no resonance on this structure due to not needing any pi bonds anywhere, because you have all single bonds. Third, we're going to talk about the VSEPR formula, which is A, on the central atom, you have 4 bonds and 1 lone pair, so E. Step 4, the electron geometry. This is trigonal bipyramidal. The molecular geometry is going to be seesaw. And this is the drawing of the model that has the dipole moment arrows and partial positive and negative signs on them. And F is more electronegative than the sulfur, so the arrows are pointing towards the fluorine coming from the sulfur. Next, we have the polarity, and this is polar due to an odd number of lone pairs, because there's only 1 lone pair on this. Thus, it does not cancel out. Step 9, the bond angle. This is going to be less than 120 degrees equatorial and less than 90 degrees axial. Next, the intermolecular forces are going to be dipole-dipole and London dispersion force. Step 11, the boiling point of this structure is going to be low. Step 12 will be, or the intramolecular force of this will be covalent, because you have 2 nonmetals. You have sulfur and fluorine. Next, the bonds of this one will be single weak bonds, and they're also single long bonds. They're not short like a triple bond would be. Step 15, the formal charge on this will be the electrons of sulfur, 6, minus 4, the outside bonds, minus 2 for the lone pair would equal 0. So the formal charge on this will be 0. Step 16, it will dissolve in water, as water is polar and SF4 is polar, and likes dissolve likes. 17, this is an extended octet due to more than 8 electrons on the central atom. You have 4 bonds. Each of these is 2, 4, 6, 8 electrons, and then you have the lone pair, which would be 10. So you have 10 electrons on the central atom, so it's extended. Next, we have hybrid orbital. For this is going to be sp3d, and you get that from adding the lone pairs, 4, plus the lone pair, 1, so that'll be 5 in total. Then we have 4 sigma bonds and 0 pi bonds, as no pi bonds were needed for this structure. And finally, we have the bond order of this will be single, as there are no double or triple bonds required for this.
I'm Trevor OSullivan, and our next molecule is S2Cl2. Please note that the following molecule contains 2 central atoms, so there will be 2 answers for each. We first begin by drawing the Lewis dot structure for S2Cl2, where we take the valence electrons to make bonds with them between the atoms, then we distribute any leftover valence electrons amongst the outside atoms, Cl, and then we take the leftovers of those and distribute them on these central atoms. And by simply looking at the Lewis dot structure, we can see that there are no resonance bonds because there's no need for a double bond in any other spots. From there, we move on to identifying its VSEPR formula, A representing the central atom, X representing the bonding groups, which contains 2, and E representing its lone pairs, which is also 2. From there, we can identify its electron geometry by simply adding X and E together, getting 4, which is tetrahedral, as referenced to table 10.1. And from there, we can identify its molecular geometry, which is bent, the 2 different atoms pulling on the central. And after identifying those, we can then draw a diagram depicting the dipole movements and the partial positive and negative signs, Cl being the most negative of the 2, so the arrows will be pointing towards it, and it will be partially negative, thus sulfur being partially positive. After that, we identify its polarity, 2 different polarities, molecular and bond polarity. Its molecular polarity is polar. By simply looking at the molecule itself, it is not symmetrical. Bond polarity is also polar due to its dipole movements, atoms being stronger than the other, thus pulling it farther. Then we can look at the molecule and identify its bond angle, which would be less than 109.5 degrees, as also referenced to table 10.1. After identifying that, we can move on to finding its intermolecular forces, being LDF and dipole-dipole, since it is a polar molecule. After that, we can go on to identifying its boiling point, which would be a low boiling point due to its low intermolecular force, dipole-dipole. Next, we can identify its intermolecular force, which would be covalent because it is two nonmetals bonding together. After that, we can look at the molecule and identify its bond length and strength. Its bond length is going to be a single long bond, since there was no need to make any double bonds. Then its bond strength would also be weak since it is longer. After that, we can identify its formal charge, which would be taking its valence electrons, subtracting how many electrons are used in groups, then how many electrons not used in bonding groups are used, and thus we get its formal charge, which is 0. Looking at the molecule, we can identify whether it's being dissolved in water or not, which would be yes, because water is also a polar molecule, so like molecules will dissolve together. Then we can look at the molecule and see its type of octet, which would be a complete octet because it has 2 lone pairs and 2 bonding pairs, which would make it completely octet. After that, we can take and find its hybridization, which is where you distribute the electrons in the molecule among the hybrid orbitals, which in this case will be sp3. Then we can look at the molecule and identify its bonds. Now in this case, since we didn't need to make a double bond or a pi bond, we can go and just say it has 2 sigma bonds or 2 original bonds. And then after that, we can look at its bond order, which would be a single bond order. Only 1 bonds were needed for the molecule.
Hi, I'm Jacob Doublesin, and I will be presenting the molecule CH3OH. So first we are to do is to draw the Lewis dot structure. So you add up the valence electrons and you get 14, and you subtract 10 with what you have with the bonds, and you have 4 left, which you put as lone pairs on O. And then next we discuss our resonance, and there is no resonance because there is no need to create double bonds with any of these. Now our VS-EPR formula, since there is 2 central atoms, we will have 2 of everything as well. So for C it is AX4E2, and for O it is AX2E2. Then our electron geometry is an octahedral for the C and a tetrahedral for the O. Our molecular geometry is square planar for our octahedral and bent for our tetrahedral. Now they're both polar, obviously, because if you look at our little model here, it is not very symmetric because none of these are the same, therefore they pull differently. Same with the O. Move on to our little diagram here where it shows our dipole moments and how the H's are being pulled towards the carbon. This H is being pulled towards the O, and the C is being pulled towards the O because of the different electronegativities. Then we go on over here, and the bond angle for C is a perfect 90 degrees, and the bond angle for our O is less than 109.5 degrees. Now our intermolecular forces for both of them are exactly the same. They are both dipole-dipole and London dispersion force, or LDF. Next, we go to their boiling point, and they both have a low boiling point because dipole-dipole and LDF are the lowest intermolecular forces you can get, and lower the intermolecular force, lower the boiling point. And then next, after boiling point, we move to intramolecular force, which is going to be covalent for all of these because it is all nonmetals with nonmetals. And for the bond length, it is a single long bond for both because there's no double bonds. And for bond strength, they're both single weak bonds because single bonds are the weakest of the bonds. Now for the formal charge on the central atom, it is 4 minus 4 equals 0. And then for oxygen, it is 6 minus 2 minus 4 equals 0. Will these dissolve in water? Yes, both will dissolve in water because they are both polar, and water is polar, and likes dissolve likes. The type of octet these will both have is both a complete octet because they both have 8 electrons. And then next we have what hybrid orbital it is, and you add your X and your E from your VS-EPR formula to get your numbers here, and then you distribute it to the orbitals accordingly. And then for the type of sigma and pi bonds, C has 4 sigma bonds, 0 pi bonds, because there's no double bonds. Likewise with oxygen, except it has 2 sigma bonds and no pi bonds. And our bond order, since there is only single bonds, is just 2 single bond orders.
I am Trevor OSullivan, and I present to you our next molecule, NH2CO2H. First, we start off, as the others, is drawing the Lewis dot structure. Now we have 3 central atoms, being nitrogen, carbon, and oxygen. So that makes up 3 different groups to make up the molecule. We distribute octets to the surrounding atoms, however not to hydrogen, because they only require a duet, not an octet. However, little oxygen out here does require an octet. So we place 8 on there. We have a total of 24 valence electrons. However, we only use 8. A little 8 on the little oxygen right over there, all lonely. And so we have leftovers. So we distribute octets accordingly to the rest of the central atoms, being oxygen, nitrogen, and carbon. However, in order to do that, we simply move one of the pairs of the valence electrons to make a second bond, which is known as a double bond. And it's not a resonance bond, and this molecule has no resonance because that is not optional. That's needed. And next we go on to the VSEPR formula. And as I said, we have 3 central atoms. So for all these steps, I did three different ones accordingly to the central atoms: nitrogen, carbon, and oxygen. So starting with nitrogen, we have AX3E. A being the central atom, nitrogen, X being the bonds, which we have 3 of, and E being the lone pairs, which we also have 1 of. Carbon, AX3, no E because there are no lone pairs associated with the carbon element in this molecule. Oxygen, AX2E2. Next, we move on to the electron pair geometry. Nitrogen being the tetrahedral, carbon being the trigonal, that's trigonal planar, and oxygen being best buds with nitrogen, so not so lonely after all, they're also tetrahedral. Next, we move on to the molecular geometry. Nitrogen being trigonal, that word, pyramidal, and the same for carbon, trigonal, pyramidal, something, and oxygen being the odd one out, again, tetrahedral. Next, we move on to drawing the model. We drew the model. We have the 2 hydrogens going away from the viewer. We have the partial positive moments between hydrogen. And then we move on to whether or not it is a polarity. Yes, it is polar. Just take a look at the ugly thing. Next, we go on to the bond angles. Nitrogen. Nitrogen is, in fact, they're all best buds in this category. They're all less than 109.5 degrees. Next, we move on to the intermolecular forces. Nitrogen having H bond dipole and London dispersion force. Carbon, the odd one out, being dipole and London dispersion force. And oxygen, again, best buds. He's coming in, what is this, the 3rd time now? Best buds with nitrogen, the little copycat. Hydrogen bond, dipole, and LDF. Next, we move on to the boiling point in increasing order, being carbon first, nitrogen and oxygen being the same boiling point. We move on to the intramolecular force being covalent because they are nonmetals. Then from there we move on to the increasing bond length, which is just like the increasing boiling point. The bond length in increasing order, carbon and being least, and nitrogen and oxygen being the same. Bond strength in increasing order, carbon being the least, and nitrogen and oxygen copycatting each other, just getting annoying. We move on to the formal charge, and they just party here because they're all 0. Nitrogen, 5 minus 3 minus 2, 0. Carbon, 4 minus 4 minus 0, 0. Oxygen, 6 minus 2 minus 4 is 0. Loop-de-loop down over to this little dude over here. Dissolve
In water, yes, they do dissolve in water because they are both polar. The molecule NH2 CO2H is polar, and water is also polar. Then we bibbity bop boop over to this guy here, the type of octets. They're all complete octets. We go down to the hybrid orbital. Nitrogen 3 plus 1 is 4, so we use sp3. And then carbon 3 plus 0 is 3, so that is sp2. Then oxygen 2 plus 2, 4, sp3. We move on to sigma/pi bonds. There are 6 sigma bonds, or original bonds. There is 1 pi bond, or double bond. Then, last but certainly not least, bond order. Single, double, bond order. Good night.